Oh, I had to fix my camera. Hi, everybody. Welcome to Computer Science 6980. So for those of you who are in the class, this is not a regular thing. This is not a remotely delivered lecture. I'm just doing this because of the university closure today for the snowstorm that we're having. So if you can hear me fine, I think you can. Just say something in the chat so I can keep going. And before I get on with this lecture, I did actually have, so this is the second lecture of the term. We had the first one in person, but I did have a number of questions from students who were not able to make the first lecture. Great, so people are saying it's fine, that's awesome. So I just want to go over this post that I made. So this is the D2L shell for the course. And I just wanted to go over this information for everybody so that you're 100% clear what's going on with this course this term. So let me just read this out. I've gotten a few questions from students who are not able to make the first lecture of the class. So this class, for people who are not officially registered, just watching online on my YouTube channel, you may be wondering, what the hell is Computer Science 6980? Well, this is the graduate version of Computer Science 3200. So this says this here. This is the graduate version of Computer Science 3200. Think of this course as like a superset of the content of Computer Science 3200, but because it's a graduate course, we will have harder assignments, we will have a course project, and we'll have about 10 to 20% more information. But this class is an in-person class delivered in like physically in person on campus. I had a couple of people emailing me thinking that this class was going to be remotely delivered, but it is not. And also I had hoped to record the lectures in the classroom if it was physically possible for me to do so, but the lecture capture availability in that classroom is just not up to the standards that I would want to have for you. And so as sort of a backup for that, what you can do is you can go to my website, to the teaching portion of my website, which I'm on right now, and then the lectures for Computer Science 3200, which is a remotely delivered course, are available online. So as you can see here, for Computer Science 3200, we do have the same topics in the course. So for example, if you wanted to go over, hey, what is heuristic search or reinforcement learning or genetic algorithms, all of these lectures are available to you. However, it's very important not to think that that is a replacement for showing up to the in-person lectures for 6980. Do not use the availability of the 3200 lectures as an excuse to skip the in-person 6980 lectures, as some material will be different, and the assignment and project instructions will be different as well. Only use it as a tool to review parts of lectures that you did not understand fully in 6980 or study for the exam. So in order to clarify that for the assignments, my assignments in this class take a little bit of explanation. There are some moving parts to the assignments. And so, for example, if you could not make it to the live lecture for, say, assignment 1 in 6980, you can go watch the assignment 1 lecture for 3200, but there will be extra parts to the 6980 assignment that you will also have to do. So just keep in mind that the lecture in person for 6980 is what you have to do, and any similarities to 3200, I'm going to say, are like purely coincidental, just for my own sanity. So you can't say, oh, but the lecture for 3200 said we have to do this. Well, that's not the authoritative thing that you have to do for 6980, okay? So it is what you have to do in class. I just want to make that abundantly clear for that. And so I hope that clears things up, and don't forget to join the Discord server for the class, because I've already posted some information on the Discord server for that. Okay, if you do want to view the lecture slides, all of the PDF slides for the class are available under the course content, under the lecture slides section. So here you will be able to see, for example, what I gave in the last class. And also, again, for people who didn't make it to the first lecture, wherever you see 3200 anywhere in this course, it's just because I didn't want to have to make an entirely new set of slides for this course. This course used to be sort of piggybacked, we call it, on 3200, where the undergraduate course lectures will be given to the grad students and the undergraduate students. So wherever you see 3200 in the 6980 D2L, please don't be too confused. It's just because I didn't want to have to make a whole new set of slides. If we also go back to the course content, under the important links section, you can see the course syllabus and the course spreadsheet. So in the course spreadsheet here, I will also link to the PDF files for all of the lectures for this class. So this schedule here for 6980 will contain all of the PDF links for all of the lecture slides that are given in person. So all of these PDF files are modern, up-to-date 6980. Wherever I do, if I do, record any lecture for this class, it will be posted here to this spreadsheet. So for example, right now you're seeing this link blank, but right after the class, I will post this video, it will be on YouTube and it'll be linked there. So I hope that, that this clears everything up and that we could actually get started with the lecture now. So any questions that you have, feel free to type them in the chat and I can respond to them as I see them. So here we go. Here is the lecture for today, and I'm going to hop right into this lecture. So let's get started. Oh, what's happening? 1 second. My monitor turned off, and sometimes what that does is it messes up the monitor input. So I just have to switch this real quick. It should turn black. There we go. Now we're all fine, and you should see the lecture. Perfect. All right. So lecture number 2, again, this is 6980. It's just that the slides say 3200 on it, but it's the same content. So lecture number 2, agents, actions, and environments. So just as a quick note, this is probably the most dense lecture of the course. Not dense in terms of ignorant, but dense in terms of just the amount of definitions and stuff. So don't worry if you don't understand completely like right away as we're going along live. Things that are said in this lecture will be explained more in future lectures, and you can use these slides as a reference for the rest of the class going forward. So this is just, hey, here's all the definitions we're going to be using in the class right up front so that you know what we're talking about as we do the more advanced lectures. So first of all, what is an agent? This was called agents and environments, and so what is an agent? So an agent is something that exists in a specific environment. So for example, if we're talking about the real world, I am an agent in the real world, right? I am an agent that exists in an environment. The agent is the entity for which we want to make decisions and take actions. So for example, I had to make a decision about what I was eating for breakfast, or where I'm walking, or the next words that I have to say for this lecture. If we're talking about a different problem, let's say we're playing I don't know, Super Mario Brothers, then maybe the player of the game is the agent and the environment is the game that they're playing. So in most cases, the environment defines the problem and the agent defines a solution. So for example, maybe we're trying to solve a maze, right? And so the maze environment would define the problem, like the start and the goal, and then the agent would be the algorithm that tries to solve that maze. And there are many, many, many types of agents. So let's look at a few. So an agent, for example, a Roomba, this self-driving vacuum cleaner robot that you may or may not be familiar with, it would be considered an agent. And the problem or environment, so the environment in this case might be your apartment or your house, and the problem that that agent is trying to solve is maybe move around and vacuum the apartment. Here we have an example from Boston Dynamics of an agent called Spot. And so Spot is this robot dog that has all these attachments that do really cool things. So in this case, Spot would be the agent and the office here would be the environment. As we move on into more like sort of well-defined computer-y problems and games, we see here is a problem called the balance cart problem, which we'll talk about more as we get into reinforcement learning. In this case, the agent is the actual cart itself that's moving left or right to try and balance this pole. And the environment is the space that it can move around in, right? And the problem here is just trying to balance the pole for as long as possible. If we have a game like chess, for example, here we have two players playing chess, so each of these players would be an agent in the environment of playing chess. And so the agent really depends on the problem. So what is the agent over here in Mega Man, for example? Is it the dragon? Is it the player? Well, that's going to completely depend on the problem that we're trying to solve. In one case, it might be the player. In one case, it might be the dragon. Say, for example, if we've been put in charge with writing the AI system for this game, maybe we care about the dragon making decisions. If we're writing a program to try and play Mega Man, then maybe the player is the agent that we're trying to make decisions for. And so it really is contextual what the agent would be considered, but it's the thing that we want to make intelligent decisions for. So an agent within an environment will take actions to achieve a particular goal, right? And just to reiterate, something else that I said in the first lecture in person is that the slides for this course have a lot of text on them. And the reason for that is not because I'm like super lazy or I just like reading from slides. In fact, I don't like reading from slides that much. But in order to save you having to go out and buy 10 different textbooks, what I've done is I've made the slides the study material. Okay, so you do not have to take notes because the notes are in the slides themselves. And so that's why some of the slides are a little bit text heavy. So an agent, I wrote down the definition here so that you can study for an exam and tell me what an agent in an environment is, for example. So an agent within an environment will take actions to achieve a particular goal. The agent perceives its environment somehow and makes a decision about which action to take. So perceiving here is related to this idea of sensors, right? So the agent is going to look around if it has visual sensors. Maybe it will smell something if it has sound, olfactory receptors. And it's going to try and make some decision about what action it should take. The agent is going to take its action or actions, which is going to change the environment somehow. In the very least, the agent might move around, for example, and then this process repeats. And so one of the ways that you could look at artificial intelligence is that AI is sort of the algorithmic discipline of making these decisions more intelligent. It's one way of looking at it. So, agents and environments. Now, to be fair, not every problem is immediately intuitively describable as an agent in an environment. For example, you might have some AI problems which are identifying apples in images, right? So you might say, well, what is the agent in that environment? Like, there's not anything that's really moving around. Like, I've sort of cherry-picked the good examples here. But in that case, the agent would be the decision-making thing, right? So the algorithm that you're trying to use to identify apples versus oranges in an image. The environment would be, say, the image set in that case. And the goal would be to get as high a percentage as possible. And so you can phrase most problems within this agent and environment mindset. So agents and environments, what does this look like for some problem-solving techniques? Well, we're going to have an environment, right? Environment is a place where an agent interacts, and we have this agent over here minding its own business. The agent is going to say, look at the environment and say, okay, I believe I'm in this state of the environment. It's going to take some sort of actions. Those actions are going to modify the environment somehow. Maybe I took this chapstick and I moved it over here. That's an action in an environment. And now the chapstick is in a different place. Then the agent is going to make some observations based on the new state of the environment, and then it's going to take new actions, etc. And so this loop is going to continue on and on. Now, this way of looking at it is more of a reinforcement learning. Like this ties really into reinforcement learning at the end of the course, but we can look at our simpler non-machine learning algorithms as this sort of framework as well. Okay, so agents. Let's get into the definition of agent a little bit more. So agents perceive its environment through sensors, right? So if we have a robot, for example, that robot is going to have some sort of way of getting information from the environment into its memory, right? So maybe there's a camera and we have visual information, or you have a laser so I can tell how far away something is, or sonar, etc. Humans, we have probably more than 5 senses, but 5 physical senses that we've grown up and known is like, taste, touch, smell, sight, sound. I think that's it. Those are the 5. Yep, I've said them correctly. So that's how I can perceive my environment. Like I know that I'm about 1 meter from my screen. I'm standing in front of a microphone. I can see all that. I can touch it. Those are my sensors. Now, some problems, you may not actually have sensors. You may just be given the state of the game. So for example, if you're writing an AI algorithm to play chess, you probably won't have to have like a camera looking at a chessboard, right? You just have some computer simulation of chess, which implements the game rules. And as such, you will just be given the game state directly in RAM, right? But that's sort of a special case where you're just given the entire game state. But in general, you do have some sort of environment that you're going to perceive with sensors. And then the agent is going to act on the environment with actuators. So if you actually have a physical robot, like I can pick up my cell phone, I have an actuator. That's my arm. An actuator is something that lets it interact with the environment. So robots would have wheels or tracks or arms or lasers or guns or whatever you have on a drone these days. Humans would have limbs. We might have tools we interact with. In games, however, again, like if we have like a computer game or like computer chess is a good example of most of these things, we would just have some predefined rules, and an action might be take a piece from here and move it to this place on a board. Now, the computer would not have a physical actuator, but it would modify the game state in order to affect its action in the actual environment, right? So we don't always have physical actual actuators, but we can simulate that in our games. And in addition to this, agents may or may not have some pre-existing knowledge about the environment. So for example, if we were to play chess and we were going to write an AI to play chess, maybe we would tell the AI, hey, here's the legal moves that you could do at this state, right? Or here's what maybe here is a queen on the chessboard and that's worth a lot. Try not to lose your queen. Right? But we may, just throw some reinforcement learning algorithm at it and say, okay, try things. And if it's a legal move, see if it's good or bad, right? So it may or may not have some knowledge about the environment. Percepts. So a percept is kind of the technical term that we will never use again after this lecture, which means it's an agent's perceptual inputs at any instant. So this is the agent's current belief of the world, and from the point of view of the agent, this is the environment's current state, okay? So a percept, let's say you have a visual sensor, a percept would be a still image, right? That is my instantaneous belief of the current state of the environment, or a chessboard, for example. A percept sequence would then be the complete history of everything the agent has ever perceived so far. So if we're talking about visual sensors, maybe a percept sequence would be a video of the entire time that the agent has been running, right? So you'd have that entire state history or visual history. Or if we were playing a game like chess, it would be like the series of states of the entire game. So what was the starting state of the game? What was the first move, the second move, the third move, all the way up? So a percept, again, is sort of an instantaneous snapshot of the current state, and then the sequence of percepts is going to be the complete history of this problem so far. In general, meaning that if you think of any possible problem that exists in an environment, in order to solve that problem perfectly, an agent's choice of action at any given instant can depend on the entire percept sequence to date. So what this means that in some problems, what you did in the past actually matters, right? In this course, however, we will only look at problems where the current state is sufficient to decide. And so these are fully observable states that we're going to be dealing with no state history required. And so the agent's behavior is given by an agent function. That's what we're giving. This agent function is essentially the brain of the agent, which maps a percept sequence to an action. So what that means in plain English is that our AI system is basically going to say, given what I've seen so far, I think we should take this action. Okay, that's what all of this means. So here's an example of that. Let's say we have this image, right? So here I have an image. There seems to be a person in midair, right? Now, I'll ask you out in the chat, and feel free to type in the chat. If I were to ask you, what does the next state of this environment, maybe, let's say, a half a second in the future, what does it look like? So what do you think it looks like? How could you describe 1 second from now if this is your current belief of the environment? Someone's got to be awake out there. Come on, type something. Okay, so someone said that this person might be closer to the water. That's a pretty good guess, right? So let's say that the problem is I want to design an AI agent. Someone said a big splash. Yeah. So I want to design an AI agent to like catch this person, right? Now, so if I want to be able to catch that person, can I just rely on this image? Well, the answer is no, right? Because if I want to catch that person, I don't know what this person's current trajectory is, right? This person could be moving upwards. There could be a trampoline down here that I don't see, right? They could be going upwards. They could be coming in from this direction. They could be coming in from that direction. I have no idea, right? So in order to make the decision in this problem of, say, setting up a net to catch this person, then my instantaneous snapshot of this, my percept, the one state is not a sufficient amount of data to solve that problem perfectly, all right? Because of this, right? Something like this, if I had like the first 5 or 6 of these, I could probably tell where they were going to land down here. But I can't just from having one image, right? So what I said earlier is that we will be dealing with problems in this course like chess, where the current state of the chessboard is a sufficient amount of information to make the perfect move. Believe it or not, it makes absolutely no difference what any of the moves previously in a chess game were. All you need to know in terms of how to make the best decision possible is where the pieces are on the board right now. Now, with the exception that in chess there's a clock, so let's throw out the clock, right? We're not looking at the clock. And also there's a thing in chess where if you make like 50 of the same move in a row, then technically it's a draw. And so you might have to have some sort of counter over on the side saying like, how many moves in a row have we made of the same thing? But you know what I'm talking about. A chessboard is our percept of the instantaneous belief of the state of a chessboard is enough to make the perfect chess move after that. Here's an example from a game of League of Legends from a long time ago. This is probably like 6 or 7 years old now. If you've never played League of Legends, then all you have to know is that the blue team is over here killing this very powerful NPC called the Baron. You can see its hit points going down over time here. And the way that this works in League of Legends is that whoever deals the last hit point of damage gets the credit for killing that monster, which involves a huge buff for your team, a bunch of gold, and a huge strategic advantage. So what you want to make sure is that no matter who has done all the damage to this thing, if you're the person who does the last hit point of damage, then you get it. So what we see up here is that this team, TSM at the time, dealt all the damage to the boss except the very last hit. And the guy from the other team up here, Piglet, waited by and then fired this long-range missile to snipe the last hit of this monster. And this is like devastating. Like this would just be a win for the other team, basically. However, And you might say, okay, that's a pretty easy problem. Like he just walked up and saw that its hit points were low and shot it. But here's what this player actually saw. They didn't know the hit points of that enemy. What this person saw was a bunch of the other team, maybe 30 seconds ago, walk into this pit and start attacking. And then based on their knowledge of the environment and an approximate amount of damage per second, etc., they took a shot in the dark and hoped that this thing is going to land and do the last hit. So in this case, in order to make the proper decision, this player did have to know a percept sequence of about a minute or so leading up to this case, okay? So this just black screen here where it can't see anything is not enough information. So in general, you do need to solve any problem, there are problems that exist like this, which are very difficult, that require the percept sequence. But in this course, we're not going to be focusing on these problems because they're just too hard for this course. All right. So what is an action then? Let's define what an action is. So an action taken by an agent in a given state transitions the state to another state. Okay? So if we've ever seen a state transition diagram like this, this is the actual definition of what an action is, right? So an action says, let's say that, well, this is a state transition table. So for very simple, for very simple problems, you can construct a table. So let's say that our environment has just two states, state S1 and state S2. What this table says is if I'm in state 1 and I take action 1, I stay at state 1. But if I take action 0 at state 1, I move to state 2. And it's the opposite for state 2. If I'm at state 2 and I take action 1, I stay in state 2. If I take action 0, I move to state 1. So this is how we can represent what actions do with a state transition table. However, just imagine trying to draw a state transition table for League of Legends, right? There was just far too many states. And so this is kind of a contrived example, but for something like, I don't know, an elevator where the action is pressing a button, you could do something like this where you draw a straight state transition table. So over here is the visual way of representing this state transition table. If I'm at state 1 and I take action 1, I stay. If I take action 0, I move. So that's what this does. If you take action 1, you stay where you are. If you take action 0, you move to the other state. So in general, because this table is like, you can't draw this table for any game. It would just be far too complex. In general, the action defines a state transition function. Or it's an input to a state transition function. So this could be a successor function, it could be a table, it could be a graph, it could be whatever. And so given a state S and an action A, S prime, meaning our next state of the game, is going to be determined by the execution of this state transition function with the inputs of the current state and the current action that we want to do. So for example, if we play Connect 4, let's say this is state S, and I put my piece, we're going to talk about Connect 4 for assignment 3. So if I choose as the yellow player to put my piece in this column, then here is my state. My action is defined by this column, and then S prime is the result of me doing that action in that board state, right? So in the particular rules of Connect 4, that function will take in this column as the action and return the state having done that action. In a more complicated game like chess, I might say move my queen to this place, and then the rule function that I have would say, okay, the queen takes the bishop, so remove the bishop from the board, and then replace that bishop with a queen. So the action function may be a little bit complicated, and of course, if we're playing, a fighting game or a video game, then these actions can be quite complex indeed. They involve like creating explosions, all sorts of things that are going on in the game. And here we have a player playing StarCraft and doing many, many, many actions per second, right? So these actions can be quite complex. They can come at a surprisingly fast rate, and they can have wildly different effects on your environment. Also, you can take actions in the real world if you have a robot or if you have a physical body, and the actions of those, like the results of those actions, you may not have like state 1, state 2, state 3. It's more of a continuous space, but your actions do have effects on both the agent and the environment that it's in. So that's what an action is. Next, we have the idea of a policy. And so what a policy does is a policy is a mapping from states to actions. So this is supposed to be the Greek symbol pi. Apologies, the font on this slide is not very good. So policies are represented by the pi symbol. And if we have pi star, that is the optimal policy. So the optimal policy is the one that accomplishes our goal the best. We'll talk about that a little bit more in the next lecture. And so pi is essentially a function which, as an input, given a state, returns an action. Okay? So given that we are in state S, do action A. And so policies could be implemented in a bunch of different ways. It could be as simple as a lookup table, meaning, like, for example, if I'm thirsty, then drink. Something very simple like that, or that's an if statement, more of a lookup table. Could be some arbitrary function calculation, some really complex function that does a whole search algorithm or something like that. It could be a neural network, etc. Here's an example of a policy. This is a policy that has been visually demonstrated. So in this example, which we'll be doing in assignment 5, you are this agent in red here. And your goal is to move throughout this grid world that is blocked by these dark tiles to get to the nearest green goal tile. And so what we see here is a policy. So it says, if I am at this location, in order to get to the nearest green location, I'm going to move to the right. In some locations, you see that there are multiple possible moves, and that's because I could get to this green tile in the same amount of time by moving up or moving left. And so this is a visual representation that if I am in this state, then either move left or move down. So that is what a policy is. Here's an example policy for the game of blackjack. If you're familiar with the card game of blackjack, we'll be discussing blackjack later on when we get into reinforcement learning, so I'm not going to say the rules here. But essentially, this betting table for blackjack is a policy. It says, if I have these cards and the dealer has this card, then here is the action that I should take. And so this is a tabular policy for blackjack. Tabular meaning it can be represented by a reasonably sized table. And so this is also a tabular policy. This is another type of policy, which is represented by if statements, for example. So this is a conditional flowchart policy. So here, this is like, how do you get out of bed in the morning? So at the start, my alarm rings. Are you ready to get up? No, then hit the snooze button and delay, and then we enter this loop of decision making. If you're ready to get up, then get out of bed. Over here, I really like this one because it solves all the world's problems, right? Just a joke. But do you have a problem? If you don't have a problem, then don't worry. If you do have a problem, can you do something about it? If you can't do anything about it, then why would you worry? Because it's just going to happen. And if you can do something about it, then do something about it and don't worry, right? So this is just like a flowchart policy of taking actions. So it's just a little bit of a joke, but it shows you how policies can take forms that are not tabular. And we could think of like the output of a neural network as a policy as well. So the input to the neural network would be the state, and then the output of the neural network would be what action to do. And in the last week of classes, we are going to see how that happened in Google's AlphaGo program. Next is the concept of rationality. So a rational agent is one that does the optimal action for each possible state. And what makes an optimal action? It's whatever makes the agent the most successful. What does successful mean? Well, that requires context as well. So what we're going to have to do is define a very strict performance measure, which measures how successful the agent has been at solving a given problem. And so the rational agent has an optimal policy. Now, this is going to... You may think that optimal means the global, like optimal if you could see everything, but optimal within its level of knowledge, right? So you can act imperfectly and still be rational because you may have had a limited amount of data about your environment, right? For example, you can't see what's behind door number 2 to make the correct decision necessarily, but you could still be rational in your decision-making process. So our performance measure is going to be the criteria for success of our agent. This could also be called in some circles an evaluation function. So let's evaluate how well the agent did at solving its problem. So a typical scenario might be that an agent is placed in an environment. The agent performs a sequence of actions. The actions cause the environment to go through a sequence of states. And then if the sequence of states is desirable, then the agent has performed well, and this would mean that that evaluation is higher. So what do I mean by that? Well, let's give some examples. Here's the example of Flappy Bird, a very popular mobile game that was out a few years ago, where you play the Flappy Bird, and it constantly moves to the right, and you hit a button to make it flap, to go up or down, right? So if you were writing an AI agent to play Flappy Bird, your performance measure would be how far did you go to the right? How many pipes did you get through? And that was the exact score that was used for the game, right? So the score for a game can often be used as its evaluation measure if it has one. And so this one is just move right. If we're talking about a different problem, like pathfinding, for example, then the performance measure might be some cost of the path. So for example, it might be the path distance. So we may say, okay, I want you to minimize the cost of this path. The cost could be distance. So if you minimize the distance, you get the shortest path to the goal from a particular location. If you are an actual company in the real world, you may care about like monetary cost. So for example, fuel costs versus shortest path. So there's a very famous example where UPS actually, I think it was UPS. Yeah. So what they did was they changed, this was like decades ago, they changed their routing system so that instead of their trucks taking the shortest path, they minimized the amount of left turns in their paths. And the issue was when a truck is sitting at a left turn waiting to turn, they're burning fuel. And if you had just taken 2 right turns instead of a left turn, you may have actually gotten there and burned less fuel. So they had this new algorithm which instead of the shortest path was minimizing fuel consumption, and it actually saved them like 10 or 15% on their overall fuel costs, which is pretty amazing. Another performance measure might be time. So some things, for example, like this pole balance, this cart pole balancing problem, what you want to do, the performance measure is how long did the pole stay above vertical? Right? So how long were you able to balance this pole for? Another time-based problem might be how long did the agent live in the video game? Maybe it's a survival type game, right? And some games, it may be difficult to come up with a performance measure that's not just win the game, right? So if you're talking about like chess or StarCraft, the only true performance measure is what was your winning percentage? Did you win or did you lose? Because in the end, that's all that matters for these type of games. Now, as we get more into the course, we'll talk about intermediate performance measures, where you might say, for example, who is currently winning the game. Like, for example, if there's 10 white pieces on the board and 2 black pieces on the board, it's probably true that white is winning that game. Right? Or in StarCraft, or another game like that, if one team has 90% of the gold and the resources, it's probably true that that person is winning the game. But how might we use that sort of who is currently in the lead type of information to help us solve problems? Well, that'll be in a future lecture. But just keep in mind that the only true performance measure that we can have for games like this is who ended up winning the game in the end. So in that context, now that we know what a performance measure is, how can we define rationality? Well, it depends on 4 separate things, or at least 4 things in my opinion. It depends on the performance measure that defines the success of the agent's prior knowledge of the environment, the actions that the agent can perform, and the agent's percept sequence. And why does that matter? So rationality does not mean omniscience. What is omniscient? So you can think of, oh, excuse me, I got the hiccups. You can think of an omniscient agent like a god, right? They know everything about the environment. They know, for example, they know the outcome of actions. So for example, if I give you a dice in a game, or a die, excuse me, like a 6-sided die, and I roll it, a rational agent would probably make decisions based on the average outcome of that die roll, because it cannot predict what will happen. But an omniscient agent would know the exact outcome of that randomness. A rational agent, let's say we have a self-driving car. If you're sitting in a car, you can only see what you can see. You might not be able to see the car that's 3 cars ahead of you, but you can still act rationally given that knowledge. But an omniscient agent would know the car that's 3 ahead of you, that's outside of your vision, okay? So just because, and here's an example, just because something makes a decision that ends up going poorly doesn't mean it was irrational, right? So for example, someone comes up to you and says, I'm going to roll a die. And if that die rolls between a 1 and a 5, I'll give you $100. But if it comes up a 6, you give me $100, right? Okay, now immediately you'd be like, this is too good to be true. This must be a scam somehow. But let's just say that person was telling the truth, right? So the person is obviously going to take that bet because you have a 5 out of 6 chance of winning that bet. Positive expected value. We'll talk about expected value later in the course. So now, obviously, you shouldn't bet more than you can deserve to lose and all that. I'm talking about expected value and averages here. But what if it came up a 6, right? Was the bet still rational? Yes, because the expected value, your expected return, was positive, right? So you should take bets where the expected return is positive. It's still a rational action, but the agent got unlucky. Right? And this is one of the problems that I have with sports, for example, where in sports, especially sports announcers and sports fans, oh my God, they expect players to be omniscient, right? So your favorite sport team could take the most rational action, but if it doesn't work out in their favor, all of a sudden they're a bunch of idiots, right? I can't believe they did that. How couldn't they know that it wouldn't work out like that? But then again, another team might take this like huge Hail Mary pass in football that only has a 1 in 1,000 chance of happening, but the player miraculously catches it and oh my God, they're geniuses. No, they're not, right? So rationality depends on like the average outcomes, not the specific outcome that actually happened. Okay, I hope you can understand that concept. So now we'll move on to environments. So essentially, a task environment defines the problem, the area in which the problem will be taking place. And so then the rational agent is the optimal solution to that problem. So the specification of an environment greatly impacts the design of the rational agent that you want to interact with it. And the state is a particular configuration of a game environment. So here's an example environment, okay? So an example environment would be chess. Chess has a chessboard and it has pieces. And it has some rules. So the environment would consist of the rules and the boundaries of the game itself. Like, for example, a queen can move up, down, left, or right, or diagonally in any direction. Bishops are only diagonal. Knights can move up 2 over 1. Those are the rules or the boundaries of the game. Or sorry, those are the legal actions. There may also be some rules. Like, for example, when your piece lands on an opponent piece, it captures that piece. It also defines the starting state of the environment and also the goal state and the goal condition. So over here, this would be the starting state for a game of chess. And over here, this is an example of a state of the game of chess after so many moves. So this is a state of the world of chess. And so in a game like chess, the agent can observe the entire environment of the game. At any point, I can see the entire state of chess. And so what this does is it starts to introduce the idea that different environments and different games have different properties associated with them. And based on these properties, like for example, observability, we are going to be able to apply specific algorithms to specific environments that have specific properties, or not apply them if they have the wrong properties. So agent observation when it comes to states. For the agent, the state of the environment is based on an observation that it can make at any given time. That observation may not be a complete representation of the environment's state. That agent's state is all that it can use to make a decision. So for example, if we have the example of like a human driving throughout a city, right? Just driving, you're in the car, you're the agent. The environment is basically the whole world. So can you see the entire world when you're driving? Of course not. You might be able to see a few cars around you. You might be able to sort of determine some of their speed. But if you're an agent trying to do that, you've got to be able to come up with some instantaneous state belief of your world. You can't see everything. So whether or not an agent can see the entire state of an environment is one of the properties of that environment, and I'll get into that a little bit later. Next is the concept of a state and action space of an environment. So the state space of an environment is the number of possible configurations of the environment for a given problem. Okay, and I'll show you an example of that in a bit. The action space is the number of actions possible from a state. So for example, if I'm looking at tic-tac-toe, the first move of a tic-tac-toe board, I can place something in 9 different places. So I have 9 actions. If I'm in a grid world environment, maybe I can move up, down, left, or right. So if I can move in 4 different directions, the action space would be 4. And what the state and action space are used for is an estimation of the complexity of a problem. So let's look at an example. Here's an animation that's playing on its own of the state space of the game of tic-tac-toe. So here's the state space calculation. In tic-tac-toe, you've got 3 possible values for a place on the board: X, O, or blank. You've got 9 possible spaces on the board, each of which can hold an X, a 0, or it could be blank. So you've got 3 to the power of 9 possible states of tic-tac-toe board, right? That's the maximum number of states you could have in tic-tac-toe is 10 to the power of 4, approximately. So what this tells us, if the state space of tic-tac-toe is 10 to the power of 4, so let's just say that is, 10,000, we'll say. Do you think we could come up with an algorithm to enumerate all of the states of tic-tac-toe? It's trivial, right? Computers can do way more than 10,000 calculations in a reasonable amount of time. And so the complexity, if the state space complexity of a game is within the reasonable bounds of computation, then that game is really not that complex, okay? Let's move on to chess. Let's do the state space complexity calculation for chess. We've got 64 spaces on a board and the number of ways to order them, 32 empty board spaces, 8 pawns in 2 sets, 6 pieces in 2 sets, and so if we do a rough calculation, we've got 10 to the 43 possible states of chess. So that is the state space complexity of chess, and 10 to the 43 is way out of our computational bounds currently, right? What is that? 10 to the 10 is a billion. And so 10, that was a billion times a billion times a billion times a billion. It's a lot of numbers, right? We can't possibly do that. Let's look at a game like Go. So we've got 3 possible things that can go into any board space. 19 columns, 19 rows, 19 times 19 is 361. We have 3 to the power of 361, which is approximately 10 to the power of 172 right? So let's put this in perspective. The number of atoms in the universe is approximately 10 to the power of 180, right? So we couldn't possibly enumerate all the states of Go. So the state space of tic-tac-toe is approximately 10,000. 43 is 10 tredecillion. I didn't even know that was a word. 10 to the power of 43. Go is 10 to the power of 170. StarCraft is 10 to the power of 10 to the power of 1,000. It's insanely complex. And so we can't, like, this doesn't necessarily mean that the game is impossible to solve, but it's a rough measure of, could we just possibly enumerate all the positions and solve the problem? So maybe if we're trying to solve a problem, if someone at a company gives us a problem to solve, we could say, well, could we, as an initial calculation, is it just like 10,000 possible things? If so, just try them all. It's easy to solve. If it's bigger than that, we're going to need to have we're going to need a bigger boat, right? We need to have an algorithm that works on this somehow. Okay. We also have something called game tree complexity, which we'll get into in a future lecture. But essentially, if this is the number of possible configurations of a chessboard, this number is the number of possible different ways to play a game of chess, right? Because if you think about it, a bunch of different action sequences could lead to the same state. And so this is the number of different action sequences for a game of chess and a game of Go, but this is the possible number of resulting board states. So this is even bigger, like way, way, way bigger. So if the number of atoms in the universe is 10, actually I have that in a slide coming up. So let's look at 360 and say, could we ever possibly enumerate 10 to the power of 360? Well, 10 to the 9 is the number of seconds in a century. 10 to the 11 is the number of humans ever born. 17 is the age of the universe in seconds, okay? So if we could do 10 to the 340 calculations per second since the beginning of the universe, we'd have a chance. 26 is the diameter of the universe in meters. 30 is the stars in the universe. 80 is the number of atoms in the universe. 122 is the number of protons that would be required to completely fill the universe, right? So someone asked, is state space complexity always in base 10? In these slides it is, right? So I've defined this in base 10. So let's just look at this. If the universe was filled with protons, and each of those protons had, let's see, a supercomputer capable, oops, I'm going ahead of myself. I'm going the wrong direction. I apologize. Let's look at okay, I finally got here. 172. If the universe was filled with protons, and each of those protons had a computer in it, and we subtract 122 from 172, so we got 50 left. We subtract 17 from that, because that's the number of seconds since the Big Bang. So if each of those computers was capable of doing a billion, so if every proton in the universe could do 10 to the 35 calculations per second from the beginning of the universe, maybe we could enumerate the positions of Go. Okay? Now, here's an interesting counterexample. So you might see this number be really large and infer from that, oh, that means the problem is difficult. Well, that's not necessarily true. Let's take the game of Go. So in Go, it's a very complex game. You place pieces on the board, you capture other pieces, and the interaction comes from the capturing other pieces, etc. Go look up the game of Go if you don't know the rules so that you'll understand the following statement. if you take the game of Go, but you remove the capturing of pieces, the resulting, let's call it new Go has the exact same state space as traditional Go, but new Go is trivial to solve. Why? Because if you can't capture pieces, then whoever moves first wins. Because whoever places the first stone, there's an odd number of stones on the board. Whoever places the first stone, you just take turns placing stones. It doesn't matter where you place them because there's no capturing. And then whoever moves first wins. And so it's a trivial game to solve, even though the state space is gigantic. So what this tells you is that you cannot enumerate all the states in order to try and solve this. It is in order for a game to be complex, it has to have a large state space. But just because, so it's a necessary condition, but it's not a sufficient condition. Hopefully that's a bit clear. Someone said, since we cannot enumerate all the state space for these games, does that mean that we cannot create a rational agent for them? No, that is incorrect. Because some games, even though we cannot enumerate all the possibilities, may have very trivial formulas for solving the game, right? So for example, like I just said, a rational agent for that game of new Go would just place stones in random places on the board. Because we know that player 1 is going to win no matter what it does, and we know that player number 2 is going to lose no matter what it does. And so that might seem like a contrived example, but other examples exist that are just as valid, right? So you can't just look at this and say, oh, we can't enumerate it, therefore I can't solve it. That's not necessarily true. It just means I can't solve it by enumerating it. Okay? Another example would be me sort of saying, okay, what's 1 million times 2? If you're looking at that from the enumeration side of things, what you would do is enumerate all possible numbers, divide it by 2, and see if you get 1 million. That is one way to solve that problem. But we don't need to do that because we have a different formula, which is multiplication, in which we can just say, oh, 1 million times 2 is 2 million. You see that? Like, sometimes we don't need to apply enumeration in order to create rational agents. All right, I'm going to move on for that now. And yeah, Go is very, very big. StarCraft, like, numbers don't even get that big. Right? Like this is bigger than a number ever has to be. It's very, very, very big. So important note is that I've already said this, a large state space does not prove that a game is complex. And I already went over this example. However, it does show us that the computational complexity required to solve the game via exhaustive search is too much, right? And so we can see, okay, tic-tac-toe is really easy to do that. So the environment definition are the rules and dynamics that govern the physics, the game rules, etc., the legal actions allowed at any state, the initial or goal states that are going to be used by the problem instance, and then, based on all of that, environments are going to have several properties. And so for the remaining part of this lecture, I'm going to be enumerating all the different properties of environments that we are going to be concerned about. And these properties, I guarantee you, will be on an exam. So pay attention to these. And the properties that we're going to be talking about will have an impact on the choice of algorithm that you're able to use to solve a given problem. So the first property is observability, and we talked about this a little bit. So we're going to look at fully versus partially observable. In a fully observable environment, the agent's sensors give it access to the complete state of the environment at any given time. And so this is access to the relevant part of the state for the actions. And if we're talking about games, in the games academic literature, these are called perfect information games. You can see the entire game. In partially observable games, some of the data is hidden or occluded from the user, your sensors may be noisy, and these are called imperfect information games. So examples of this: chess is fully observable. You can see the entire game. StarCraft is not fully observable. You cannot see parts of the map that your units are not near. And so that is partially observable. You do not necessarily know what your opponent is doing. Another example might be a game of cards where I have some cards in my hand that I can see that you can't see. So that's also a partially observable environment. Deterministic versus stochastic is another property. So deterministic essentially means no randomness, okay? So the next state of the environment is entirely determined by the current state and the action of the agent, and there is no randomness whatsoever in the environment. In a stochastic environment, there is uncertainty about the outcome of actions. So that means there might be some random chance. I could roll a die, I could draw a card, I could spin a wheel, etc. In a video game, there might be a critical hit, something like that. And so there is a random nature to the environment and the actions that you can take. And so you think about it from the point of view of the agent. If I am going to choose an action to do, and the agent does not know what the state will necessarily be after taking that action, then that is a stochastic environment. So a stochastic environment would be one in which we are not certain about the outcome of actions. So if we're playing blackjack or any other card game and we draw a card, we're not necessarily sure what we're going to get. If we're playing Monopoly and we roll the dice, we're not necessarily sure what we're going to get. But in a game like chess or checkers or Go, everything is deterministic. I know exactly what will happen if I move my piece from here to there. Okay. Episodic versus sequential. So it turns out that the vast majority of problems are sequential, or the ones we're going to be studying in this course, but episodic problems do exist as well. So in episodic problems, agents' experiences and actions are divided into atomic episodes. So the agent is going to perceive a state, take an action, and the next episode does not depend on the previous episode. That's actually kind of a rare occurrence, and is more about things like classification, prediction, stuff like that. In sequential problems, the current action is going to influence future decisions. And so your actions may have long-term consequences. So an episodic problem might be a problem like image or pattern recognition, right? So whatever I think the current digit is has no bearing on what the next digit is. Now, you might say, okay, what about during training and your model is improving? I'm not talking about like training where improvements are happening, but like whatever this one digit is, that is one prediction episode. Whatever the next digit is, that is another prediction episode. Okay? Versus a game like chess, where if I make a specific action on turn 1, that has huge ramifications later on, because that will determine specific moves may or may not be legal on the next state based on what I've done in the current state. Okay, so most problems that we talk about are actually going to look like this. The next property is dynamic versus static environments. In a dynamic environment, the environment may actually change while the agent decides what to do. And so the environment is kind of like just going along, like the real world, right? So if I am standing in the middle of a street, for example, and there's a car coming towards me, that is a dynamic environment. I'm sitting there trying to make a decision, but the environment is dynamic. Whether or not I choose to get out of the way, that car is coming, right? So it's a dynamic environment. In a static environment, then the environment only changes when an agent deliberately takes an action. And so the decision-making time doesn't necessarily matter. So if you're thinking about games, this would be a real-time game versus a turn-based game. So I know I use StarCraft and chess a lot, but they're great examples. So StarCraft or other video games are a dynamic environment. If you play Counter-Strike or Dota, right? If someone's coming at you with the intent to do you harm, if you don't do anything, if you're not deciding on anything, if you're not taking any actions, well, you're just making it easier for them, right? That's a dynamic environment. With chess, your opponent literally cannot do anything until you take a turn. Now, if you have a clock in a game like chess, of course, if you just use all your time, you'll lose, but let's look at it from a non-clock point of view. This is essentially a static environment. Discrete discrete versus continuous. This distinction is applied essentially to the state space of an environment, and it determines sort of the way that time is handled in a game. And so in a discrete environment, there are a finite number of distinct states, and there are a discrete set of percepts and actions. In a continuous environment, it's essentially continuous time and continuous actions. Well, what do I mean by that? It's easier to just have an example. So in chess or in a card game, it's very discrete, right? I can have one of this many possible hands of cards. One of my actions is to take a card and lay it on the table. I can have move this piece from here to there. It's a discrete environment with a discrete number of possibilities. If you go to the real world, you have a continuous environment in which things are happening all the time. Now, there's sort of a philosophical debate at the heart of all this of whether or not the universe is actually discrete or it's actually continuous. Like, can we look down far enough into atoms and the way physics works to find like the clock time of the universe? Okay, that philosophical argument is all well and great and it's very interesting, but let's just assume that the universe is continuous, right? That there is we can break down time and space into infinitely small pieces, right? That's what continuous means. So what this means for your program is that if you are working in a continuous environment, you are probably going to have to discretize that environment somehow in order to make decisions, right? So you might say, okay, I'm going to look at the real world in a self-driving car and I'll try and make decisions every 10 milliseconds or something like that, because the computer is not physically capable of making continuous outputs unless you are using physical computation, which they actually used back in the day in like military firing computers and stuff, where like actual physical gears and cranks were moved to form the output of something, in which case you actually have a continuous computer, which is kind of awesome. But modern digital computers are not continuous. They are discrete mechanisms. Next, you have single agent versus multi-agent. So in single agent, obviously we have one agent acting at a time. This could be something like puzzle solving, so like solving a Sudoku or a crossword puzzle, or pathfinding from a goal to an end, etc. Or we could have multiple agents. If we have multiple agents, those agents are acting together somehow. They may be either cooperative or competitive. So over here, we have a single agent problem, which is like getting around these obstacles to get to the goal as fast as possible. Over here, we have a multi-agent problem where we have two teams of 5 players each. So in this game, we have 5 competitive agents versus 5 competitive agents. And so that's a multi-agent environment. Next property is complete versus incomplete information. So this is a bit confusing because before I said perfect versus imperfect information. So perfect versus imperfect information is the observability of the state of the game. This is a little bit different. In complete information, all of the game rules and physics are known, and all of the possible actions are known. But in incomplete information environment, the game rules or physics may not be known. If I have a robot and it can apply voltages to a wheel, like the exact outcome of that, I would say is not complete, right? We know pretty much what will happen, but let's say I put you into an environment like Super Mario Brothers, and I didn't tell you, hey, the A button makes you jump, the B button makes you run, pressing right goes to the right, or colliding with this thing gives you points, or doing something with this thing, you know? So you may or may not be actually given any of this information. So whereas perfect versus imperfect information was the observability of a game, complete versus incomplete information means like, do you know the rules of the game? Do you know the physics of the game? Do you know the action possibilities of the game? And when you come into incomplete information games, it's a very, very complex space, and we won't be dealing with those problems for the course. So if I were to make a table of sort of the increasing difficulty in games, or environments, you know, we sort of go on, okay, all of these problems are sequential because we're not going to be dealing with episodic problems here. So in terms of the number of agents, a crossword puzzle would be a sequential, sequential because every action affects the next action. If I put a word here, then a certain other word won't fit where that word was. It's single agent because you're just solving a puzzle with one agent. It's deterministic, meaning there's no randomness in a crossword puzzle. It is fully observable, so there's nothing hidden from me. It is static, meaning that nothing happens to the environment unless I take a move. And it is discrete, meaning that there are a finite number of things that I can do. If we then change that from a single agent game to a multi-agent game and leave the other properties the same, we get something like chess, right? Because chess is a multi-agent game. If we then add some randomness, right? So we make it stochastic instead of deterministic, then we have a game like backgammon where you're rolling dice in the game. If we then change that game from fully observable, you can see everything in backgammon, to partially observable, like a game like poker, maybe that game is even harder. But that game is still static, so let's change that game from static to dynamic, and now we have a game like StarCraft, right? Where I have a dynamic game which is acting even if I'm not making decisions. And then if I go from StarCraft to the real world, well, that's probably taking this discrete game of StarCraft and turning it into a continuous game. Now, you could argue that video games, they're acting at like 60 frames per second, maybe higher than that. And so for most intents and purposes, they could be treated as continuous games. Like, okay, we have floating point locations in our game, and the time scale is really, really small. So you could, in some world, classify something like StarCraft or video games as continuous, but we're going to stick to the strict definition that anything that can be represented in a computer is quite obviously discrete. So there we go. All right, so that was a whole lot of definitions. And but now you know it, right? So that was this lecture on agents and environments, what they are and what they do and their properties. And in the next lecture, we will start on problem solving and search. So problems have a, believe it or not, very specific way that they have to be defined in order for us to apply AI algorithms to them. So we will talk about how problems should be defined, what our goals are, etc., and get started on, hey, what actually is this thing called search that we've been hearing so much about, and how can it help us solve problems? That's it for this class. I don't see any questions that are relevant or that I haven't answered in the chat. So thank you so much for tuning in. And class, assuming the weather is fine, class is back to in-person on Thursday, and I can't wait to see you then. See you.